this video is one of the key videos of this whole course because it shows what you can do with higher order programming. So now we've defined a procedure as a procedure value with a contextual environment, and this is enormously expressive. And arguably, it is the most important invention in programming languages since they were invented in the 50s. It makes possible building large systems based on data abstraction in layers, encapsulation. Many of the good properties are based on this key idea of higher order programming, which is based on procedure values with a contextual environment. So now, in this video, let's see some examples of what we can do with higher order programming. So the first thing, procedures and functions are values. We can pass them as inputs and return them as outputs. Remember, of course, that functions and procedures in the kernel language are the same concept. A function is a procedure with an extra output argument. So when I say function, it also holds for procedures. When I say procedure, it also holds for function. So, first of all, let's define what it means, the order of a function. Because we're talking about higher order programming. What is this higher order? Well, we can define the order of a function or procedure. We start by saying a function whose inputs and output are themselves not functions. They are, for example, just integers or lists of integers. Well, this kind of a function, we say it's a first order function. It's just a function. Now we go farther. We say a function is order n plus 1 if somewhere in its input and output there is a function of maximum order n. So we take the maximum of the order in all the arguments and the output and we add 1. And when we increase the order of a program, things get more and more general, more and more abstract, as you will see. So let's give some examples to show what we can do with higher order functions. In this video, we'll give some examples, but this does not exhaust the possibility, the ingenuity you can do with higher order programming. Later in the course, you will see more examples. So the first example is a simple concept called genericity. Genericity in general is simply passing a function as input. So here's a simple example. We have the function map, which takes f, another function, as input and a list, and applies the function f to all elements of the list and returns a list which has the values of all these function applications. So for example, here's an execution. We do a map. We have here an anonymous function which takes an argument x and returns x squared, and we apply this on the list 789, and this will return what? Well, the list of squares. So 49, 64, 81, a list of 3 elements. Question for you, what is the order of map in this particular call? Well, fun here, the anonymous function that we give as input is first order because the arguments here are numbers. So map is going to be second order. So let's go to another example called instantiation. This is when a function is returned as an output. So here, let's define the function makeAdd with an argument a, and it returns another function of one argument which does x plus a. So if we call makeAdd with argument 5, we can say add 5 is equal to makeAdd of 5, and add 5 is a function that will add 5 to its argument. So calling add 5 of 100 will display 105. Notice this is instantiation. Notice that if you know object-oriented programming, you can start feeling the connection here between classes and their instances. Well, this connection is actually very strong, as we'll see later. So what is the order of makeAdd? Well, it returns a function of first order, so makeAdd is second order. Another question, what is the contextual environment of the function returned by makeAdd, of this function here? Well, the contextual environment contains the identifier a and the variable that a is bound to. So for add 5, a variable bound to 5. So let's go to a third example, function composition. We will take two functions as input and return their composition. So this is a function compose, which has functions as input and a function as output. So for example, we call compose here with a function, an anonymous function that squares its argument, and an anonymous function that increments. So what does f new of 2 return? Well, we're going to first do g of x, which is 3, and then f of 3, 3 times 3, returns 9. Going a little bit farther, what does applying the function compose f new to the value 2 return? I'm going to let you figure out that answer. And a final little question, what is the contextual environment of the function returned by compose? Well, clearly this function here, returned by compose, has two identifiers that are used inside and defined outside. So the contextual environment contains f and g. Now let's go even farther. There is some concern with single assignment that it will require you to create many variables, identifiers, and clutter your program. This concern is completely ill-founded. Let me show you an example. We can hide an accumulator by using higher order programming. So let's say we want to sum the elements of a list. We have a list A0, A1 up to an-1, and the sum is going to be A0 plus A1 up to an-1. Let's write this sum in this way, left associative. So we have 0 plus A1, and then we add A as a plus 0 plus A0, then we add A1, then we add A2, and so on, up until adding AN. Replacing the plus by a generic, by any function, f, we have this, f of 0, A0, given in an argument to f with A1, and so on, up to AN. We can define a function that does this. This function has a name. It's called fold L, L for left associative. So we can say S is equal to fold L, and here we have the list, and here we have F, and here we have the initial value 0. Notice no more accumulator. It's hidden inside the fold L. So here's the definition of fold L. It takes a list argument, a function argument, and an initial value argument. It's simply going to do a case. At the end, it returns u, and for each element, it will do f of u, h, and then it will continue. So this will be the accumulator. So the argument u is the accumulator, and here, for example, is a way to call it for doing the sum of the elements of the list. So the list 5, 6, 7, an anonymous function that does x plus y, and initial value 0, and this will return the sum of the elements of the list, which in this case will be 18. Okay? Let's go on. We have by far not exhausted the abilities of higher order programming. Here's an interesting thing we can do. We can hide a value inside a function. This is kind of a trivial example, but it will become very important later for data abstraction. So let's take a function here called 0, zero argument function, but it returns the number 0. Let's take a function inc, which takes h, which is h is a function that hides a number. It exposes the number by calling the function, it adds 1, and it returns a new function which hides that result. So then we can say, for example, 3 is equal to inc of inc of inc of 0. So 3 is a function that hides the number 3. If we do browse of a call to 3 with no arguments, we will display 3. So you notice that the functions are hiding things inside them. This is the foundation of encapsulation. This is a trivial example, but it's going to become much more important when we combine it with other techniques and use it in data abstraction. And a final question for you. what if I define the inc function as follows? Instead of doing the calculation h plus 1 and then creating the output function, I do it inside the function I create. So the function inc h will return a zero-argument function that does applying h plus 1. What's the difference between these two definitions of inc? Think about it. Another example of delayed execution. We can define control structure. Here, let's define a kind of if statement. So if true, if this condition is true, then we execute statement. Condition and statement will be, respectively, a zero-argument function and a zero-argument procedure. And inside if true, I apply cond. I say if the result of cond is true, then I execute statement. And then I call it. Notice how interesting I can call it. Statement is a zero-argument procedure. In this zero-argument procedure, I can put any statement I want, anything I want to execute. It will not be executed when I declare statement, but it will be executed possibly inside the if true. And then the condition here, I put any Boolean expression, 1 less than 2, inside a zero-argument function, and it will be evaluated inside if true. So you see, I have made the difference between declaring a function or procedure, which wraps any statement or expression, and then I decide to execute that statement or expression later. Okay? This can be used to build control structures. If statements, while loops, for loops. You don't actually need to invent those in a language. If you have higher order programming, you can create your own sophisticated control structures. Okay, well, let's stop giving examples for now. We will see more later. So we have given 6 examples to illustrate the expressiveness of higher order programming: genericity, instantiation, function composition, abstracting an accumulator, hiding it, encapsulation, and delayed execution. When we start talking about data abstraction in detail, we will use these techniques and others. Data abstraction is built on top of higher order programming.